Hello everyone, I'm Yashwant from Amazon and I'll be presenting our work Generative or Discriminative, Revisiting Text Classification in the Era of Transformers. We revisit a long-standing question in the field of machine learning. How do generative and discriminative classifiers fare against each other in the context of modern transformer architectures? Generative and discriminative classifiers differ in what they learn. Generative classifiers model the joint distribution of the input and the label p of x comma y, typically written as p of x given y into p of y. Discriminative classifiers directly learn p of y given x, the decision boundary between the classes. Historically, generative classifiers learn faster with less data, while discriminative classifiers achieve lower asymptotic error with abundant data. We ask whether this classical two-regime behavior still holds in the transformer era in the context of text classification. We evaluate the following architectures: encoders, auto-regressive models, discrete diffusion models, and masked language modeling. The discriminative classifier, based on the standard transformer encoder, directly learns p of y given x through a classification head applied to the CLS representation. It doesn't try to model the data distribution, but only the decision boundary that best separates the labels. The auto-regressive classifier learns p of x given y using a causal left-to-right attention structure. To preserve this causal flow, we prepend the label token at the beginning of the sequence so the model generates the input conditioned on that label. During inference, the model must score each candidate label separately, requiring k forward passes for k possible labels. The final prediction is the label with the highest conditional likelihood. The discrete diffusion classifier appends the label at the end, but since diffusion uses bidirectional attention, label placement doesn't matter. During training, the model gradually adds noise to the text by masking tokens and then learns to recover the original sequence through iterative denoising. This process effectively learns a generative model over text. The masked language modeling classifier also appends the label token at the end with the phrase "the label is mask." It learns to predict the masked label token using bidirectional context, thereby modeling a pseudo likelihood. This approach makes it a pseudo-generative classifier. It estimates the joint distribution indirectly through token reconstruction. Unlike previous work, which only focused on sample efficiency, we expand our study to model scaling behavior, ordinal relationships between classes, output calibration, and robustness to input noise. We ask three key research questions. How do these modeling paradigms compare when trained from scratch? How robust are these models trained from these paradigms to input perturbations and noise at inference time? How well calibrated are the scores from these models? Do they capture ordinal label relationships such as sentiment? We evaluated the two paradigms on 9 public text classification datasets. We trained 3 model sizes, 1 layer, 6 layer, and 12 layer, across varying data fractions. This setup enables us to analyze both scaling and sample efficiency across classifier types. we observe a clear two-regime pattern. In low data settings, generative classifiers, especially diffusion, perform better due to their stronger inductive bias. As data increases, discriminative classifiers overtake, achieving higher asymptotic accuracy. Small models perform near random at first, but the discriminative classifier improves steadily. For large models and with enough training samples, the masked language modeling classifier dominates overall. This shows that the classical trade-off persists even in transformer-based classifiers. We evaluate the minimum amount of input noise needed for a certain degradation of model performance using random token dropping and random token substitution for all model configurations. Under random token dropping and substitution, diffusion classifiers are the most robust thanks to their denoising training objective. Discriminative classifiers maintain good stability, particularly under token dropping. Auto-regressive classifiers are the most sensitive since left-to-right generation amplifies errors. Masked language modeling classifiers remain competitive but degrades faster, especially under token substitution. Using the output scores from all the classifiers, we compute calibration error and unimodality. In terms of calibration, the discriminative classifier is consistently the best, producing well-calibrated probabilities and unimodal ordinal distributions. The masked language modeling classifier performs nearly as well in high data settings. Among the generative classifiers, auto-regressive classifiers calibrates reasonably well in low data settings. Diffusion classifiers preserve ordinal structure but lack probabilistic calibration. When pre-trained models like BERT and GPT-2 are used, the two-regime pattern disappears. The discriminative classifier outperforms all others across data regimes. Pre-training essentially provides an extremely large data prior, removing the low data advantage of generative classifiers. These results should be interpreted with caution due to the confounding effect of the pre-training corpus on these models. Based on our experimental results, we offer the following recommendations to practitioners. For latency critical use cases, a one-layer discriminative classifier is ideal. It is efficient, robust to noise, and well calibrated. For high data and offline settings, the 12-layer masked language modeling classifier performs best overall, although it's less robust to noise. For low resource setups, diffusion classifiers offer strong noise resilience, where auto-regressive classifiers are preferred if calibrated probabilities are important. Our analysis focuses on standard fine-tuning and in-distribution settings. Future work can extend this to parameter-efficient methods like LoRa, multimodal, and out-of-distribution tasks. Thank you for listening. Our results and code are available at the provided link.